It's also nice to, if we look here on the scale, it's 10 microns here. And we see that the silicon particle is about 10 microns. We measured to 14, I think. And your mark is about 2 microns from the edge of the silicon particle. And we see we have a little bit silicon signal there. So let's take a fourth measurement point and show something that's even further away, up here. Let's see what happens on that. So then we can directly compare these two. We can change the scale to logarithmic here also. That is usually nice. Yeah, this is very nice, right? So now we have the yellow is the new 0.4, and we can compare it to 0.1. And 0.1 actually had a little bit bump there. But now we don't really see anything on the yellow one there. So why is it that? Why is that? What's your guess?
It was too close to the silicon.
Yes. Even if the spot size on this machine is 50 nanometer, the X-ray area, this electrons enters in an area of 50 nanometer, but then this bunches around and creates a lot of X-rays everywhere. And they can sort of scatter so far away, so we are actually in an organic material like this. That can be several micrometers in lateral distance and also several micrometers in depth. So that means even if we are looking on exactly, the electron beam is hitting exactly at that point in spectrum 1, some electrons will scatter around inside the sample and reach the silicon and create X-rays in silicon. It's a very small signal, but although some reaches that area. So this is a very good thing to remember as a newbie on EDS technology, that this volume, the region you're getting the X-ray information from, is much, much larger than the spot size. It's in the micrometer range. The more, what shall I say, heavy elements you're monitoring, if you're monitoring like steel alloys, then that volume shrinks. But it will never be in nanometer. It's always in micrometer range. And this is like one of the major drawbacks with EDS, that you don't really have the same resolution in the EDS data, lateral resolution, so to say, as the electron microscopy image itself. And it's a very typical newbie mistake that you're measuring a particle and you want to see the composition of the particle, but the particle is like 100 nanometer. Then you're measuring the signal from the particle, but you're also measuring a big bunch of background from the surrounding of the particle at the same time. So, last part of the tab order is calculate composition. So then we come into this. EDS can do quantitative and qualitative measurements. Quantitative measurements is when you want to find out what do I have in my sample. This EDS method is excellent for that. And the strength of the method is that you can see it as correlation in which place in the sample I have what. I mean, if I have gold here and I can have silver over here, I can see that this area contains this, that area contains that. There's very few other methods that can compete with that. That is the strength. Correlate lateral structure information with elemental composition. That is the strength. When it comes to quantitative measurements, then one usually refer to this as a pseudo-quantitative method. Because if you come from a chemical background, as in your case, you were working in the chemical subject, quantitative measurements in chemistry field is very accurate methods. Usually you dissolve materials, run into different kind of solutions and spectrometers and things like that. GC, IR and things like that. They're very accurate. So quantitative measurements in chemical, in the chemistry subject is very accurate. And it should not be confused here. So that's why we tend to call it pseudo-quantitative measurements. And the reason for this is that what this machine is doing, it measures, we can take our, this was the silicon particle, so here is the silicon spectrum. Mm-hmm. And then we can put up this table here. We can take that one with the zinc. Here we have more elements to play with. So the only thing that the EDS technique is doing, it measures the characteristics X-rays, the intensity of those. That is the raw data. And then we want to translate that into how much in weight percent or atomic percent does that correspond to. But before we can reach there, that transformation is done through a mathematical model. Because it's not so straightforward. I mean, one can think that high intensity means high concentration of that element. But that is too simple. Because, what shall I say, if the element you're analyzing is more deeply embedded in the material, more X-rays will be absorbed or reflected. So that a material that is further down into the surface will look like something that is of lower concentration. So geometry will influence the accuracy of this. Yeah. And as I said earlier, rough surfaces and things like that makes X-rays scatter in different directions and enhance different X-rays. So some elements might look stronger than others. Mm-hmm. We also have an issue that the X-rays from one element can create X-rays in another element. So then we're talking about different types of fluorescence aspects. And those can sort of enhance signals or suppress signals depending on which way the X-ray is going here. So there's actually a pretty complex mathematical model to keep track of all this and try to correct for these things. But it assumes, as I said initially, that the sample is completely homogeneous, mirror flat surface. And if you don't have that, then you are tricking the model. So that is the reason why if we're taking a steel alloy and running that, we will measure 15, even 30% carbon. And no alloys contain more than 3% carbon. And the reason is that the model thinks like this, that we're measuring a carbon signal from the contamination layer on top. But the model thinks this is not a layer, it is a homogeneous structure. Yeah. And carbon has a very low energy signal. It's like 0.5 kilo electron volt or something like that. We can see it's like even less, 0.27. So that means a small energy X-ray is easily absorbed also. Yeah. So then it says, okay, if this is carbon emitting X-rays and we're measuring a lot of that X-rays, then there must be a lot of that carbon inside that steel matrix. Since steel is a very solid material around it. So then it must be a lot of carbon. And then it comes to doing the calculation, it must be 30% carbon to get that kind of intensity. But the model is full because all the carbon is on top. So there is no absorption of the X-rays. It goes directly to the detector. So then everything becomes wrong. And you must understand it. That's why we call it pseudo-quantitative measurements. So it is a model that gives us these concentrations. It's not original data. In chemistry, we get, the raw data is the concentration. But here, there is a model from the X-ray intensity signals to the actual weight percent data. And we can look here on the table. So here we can see the thing called apparent concentration. That is the concentration we get if we just look on the intensities straight on. Then it says we have 21% carbon in our case here, for example. But then we see something called the K ratio, and that is the correction factor that the model adds to compensate for all these fluorescence effects and so on, as the model tries to fix for us. And you can see if these numbers varies a lot, you see this one is say 0.001, but this one says 0.2. It's a very big change in K ratio between these two. That means the model have been treating these two elements quite severely, differently. And that is, what shall I say, it is not proof of error, but it's a sign that something fishy might be going on here. And we can see it shows the calculated weight percentage, and they all add up to 100 since we choose to normalize our data. Another thing to mention also when it comes to EDS is that it measures elemental composition atomic-wise. I mean, do we have this atomic element or do we have that atomic element? It doesn't say anything about chemical bonding.
Yeah.
So if we measuring like, I don't know, copper oxide, that should be 1-to-1 atomic-wise. Then we will measure 50% copper, 50% oxygen. And we can by ourselves draw the conclusion that this might actually be copper oxide. But there is no proof that there actually is a chemical bonding saying we have copper oxide. They could be like 50% oxygen around there embedded in some copper matrix somehow. Sounds very weird. Most likely, I guess, in this case it is copper oxide. But I want to emphasize that we don't get chemical information here. We only get elemental composition. So if we want to prove chemical bonding, we need to do like FDIR or Raman or something like that provides that chemical part. All right, we can continue. You can continue with the mouse here, and then we can choose the line scan. And we go back to acquire line directly there. And make a line that goes straight across the silicon here. And then you click start. So a line scan is, as the name implies, it measures the spectra, the EDS spectra, as a function of distance. So this is like one-dimensional data now instead of a point. And if you click on the gear there, you can see that here it says acquisition time until stopped, and it's quite common. You can run a fixed time, but most of the time you run it until you're satisfied with the statistics in your spectra. And we can see it measures 500 points here also. I can do less points than that also. 500 was a lot actually. So let's go to construct line scanner, next tab order. And then we can see here, we can remove this one also. So we can see it takes this line here and cuts it out and rotate the image. So the x-axis here corresponds to this line now. And then we can see the X-ray intensity. Remember, this is the X-ray intensity, not the concentration. And we see we measure less carbon on the silicon because the silicon is blocking the carbon that is beneath, basically. So that is what we can expect. We measure some iridium because we have coated everything with iridium. This is also nice. I mean, we're measuring iridium on top of the silicon. That means that the silicon was there when we coated it. Sometimes this is actually vital information, because sometimes you can see things and then you find out they don't have the iridium on top of them. That means that was contamination that came onto it after. So most of the time due to fingerprints and bad handling. And yeah, we see these elements here. Can one get the scale back there? Yeah, like that. You can choose to stop it there also. We can, if we look on the iridium signal also, we see it's fluctuating a lot. And when we coat, we spray, though this was 10 nanometer, we sprayed on this sample. So, and that is very uniform. It's a very high quality coating in that aspect. So the reason why we see so much fluctuation there is because of the roughness of the surface.
Yeah.
The X-rays are blocked due to obstacles and reflected in different way and doesn't reach the detector and so on. Mm-hmm. If we want to see quantitative data as a function of the line, we can choose that. It's called quant line here. Then it calculates with the model our weight percent data instead of that X-ray intensity. So now we see that part instead here. And then when I also come to, okay, how do I sort of export my data? Mm. In standard electron microscopy imaging, all data is images, and you just save the images, so that's easy. But here we have spectra, we have images, we have data tables, and what you can do on this is that there is a report tool here, but if you don't have this kind of industrial case where you do the same kind of measurement over, then you can set up a proper report. But if you are more in the academic case where all samples are unique, I rather prefer to do everything manually. So what you can do, you can always right-click on everything. So if I want this particular image, I can export that as an image. Mm-hmm. If I want this spectra, I can export it. And if I just export it like that, then I get that blue-yellow bitmap image. Mm. But in a publication, you would like to replot it in a more professional way. So EMSA is a comma-separate value data table, and then you can replot it. All right. Same thing goes here. You can choose to export CSV or as image bitmap images. So that's the way I like to do it. So I usually copy these images separately into a Word document. Mm-hmm. And bring all that with me. And if you want to have like the data table that we had on this point scan here, then you can just mark and copy and grab that with you. Analysis at the top here, that is the same as making point and ID, but you analyze the whole frame. Mm-hmm. You don't choose a point, the whole image. Take the X-ray straight from the image. The true line here is like that can be a little bit when we talked about this sodium case here, the sodium was overlapping a little bit. We decided that we don't believe that material contains sodium. Here was the spectra, right? We talked there was sodium here. Mm-hmm. So what true line actually means is that it just takes the central part of that signal. So it artificially tries to boost the resolution energy-wise of the detector. So if you have overlaps like that, it can enhance those kind of scenarios. The energy resolution of these drift detectors is, the original, we had this process time we talked about. Where is it? There, process time 5. I said when I have a higher number, it calculates the energy more accurately. Mm-hmm. And that takes longer time. But how much more accurately is this? And on the old detectors, process time had some kind of significance in this. You actually improve the resolution energy-wise by changing process time. On the modern silicon drift detectors, there is very, very little change. The width of the peak is larger than the benefit when you change that process time. So if you go from process time 1 to process time 6, you can see a little bit of improvement. But from a practical aspects, you can just use process time as a way to adjust the dead time.
Okay.
You will not get any like resolution performance boost on this in these modern detectors.